on the majorization, and then I think we're going to go on to the EM algorithm. There's actually some material at the end of the majorization section that involves, I think, parameter estimation. Is that correct? Yeah, but I think maybe I'll just kind of skip over that. There's sort of more advanced material if you want to cover their own, which I recommend you do. But yeah, question here. Do you have any questions? Any questions? Is everybody working on the lab? Okay, the exam is next Friday, right? And you'll probably be sad to know that I actually got the exam written. That means it's coming, okay?
The exam will include this exam?
I think I did everything through chapter 6, but not 7. Okay. But, okay, let me just repeat one more time. What's the structure of the exam? Homework. So what would be a really good way to prepare for the exam? Do some homework. And not just do them, but actually get the correct answers. That's critical. In the words of Monty Python, it isn't just the words you use, it's the order you put them in too. Okay? So, yeah, make sure you don't scribble random answers down that there's actually validity here. Okay? So you can help try to figure that out. You can ask me, you can email me, you can talk to each other. You can look it up on the web. Oh, I'm sorry, it's Friday. Whatever, okay? Now, are there any other questions? There's a question here I think maybe I'll answer, I'll address quickly. Okay, with the lab. Okay, so now you're doing the lab where you do the blurring, right? So with the blurring, before you had the blurring, what you had is you just had, without the blurring, you just had that you have X and Y. You were trying to minimize the mean square error, basically, between the two, subject to this constraint that you had this quadratic regularization. And then you did the non-quadratic regularization. I forget now, what's the word? You do the non-quadratic regularization first and then do the de-blurring, or you do the de-blurring first and then the non-quadratic? For the lab, in the lab. You do them both, but I forget which one you do first.
The Non-Gaussian prior is the last thing we do.
Okay, so you first do the quadratic,
Gaussian de-blurring.
then you do the de-blurring with the quadratic, and then you do the non-Gaussian case, right? Okay. Now, so here you have, I think the notation is a little bit different in the lab. Is it H instead of A? Yeah. Okay. So you have the norm, so you have y minus, I'll use A, okay? AX, okay, squared, right? Plus, then you have X transpose BX, right? Yeah. Like this, right? And you're trying to minimize this. Now, the question is, well, what's A? I give you a filter. So let's say the filter was 3 by 3, okay? So what's the relationship between this filter and this matrix? It's confusing for a lot of people. How many people completely understand the relationship between this filter and this matrix? Okay, so usually at this point, people are beginning, well, you guys have to tell me that the camera's pointing in the wrong direction. Okay, that's better. So what's the relationship between this matrix and this filter, okay? Okay, I'm not saying this to discourage you, okay? I'm just saying it, maybe I shouldn't even bother saying it, but I'll say it because I feel like saying it, okay? Which is that we've actually already talked about all this. It's just at the time, you were like, oh, you're very polite and everything. Oh, yeah, okay, I understand. But it's not until you actually go to do it that all of a sudden you go, oh my gosh, I don't know what's going on here, okay? And when you actually go to do it, you go, oh, I don't know what to do. Well, we've talked about it. Okay? When you actually do it now, hopefully this will force your brain to actually think about what you thought you already understood. Okay? So now, the thing that's confusing is this is a matrix, right? So it's a 2D object. See, I never like to call filters a matrix. I call it a 2D array. Because a matrix is an operator. This is an operator. It takes an input of X and it produces an output. A filter, well, okay, a filter kernel is a function, so I guess it can be an operator, but it's an operator because you can create a matrix out of it. It's really just a signal, okay? So I always call this a 2D array, and I call that a matrix. I reserve the word matrix for actual operators, okay? So now what's the relationship between this and this? Because this is a 2D object, and that's a 2D object, but they're different. Well, remember, X here, you have X, and you have A, right? So this is X, and this is A. A is a matrix, X is a vector. So this X is actually a rasterized version of the original image. The image is actually a two-dimensional object, but we make it into a one-dimensional object by breaking it into pieces. These are the different rows of X, okay? Now what happens is that effectively this matrix also gets broken into pieces. So there's 1, 2, 3. So each of these blocks operates on one row of input image and one row of output image. Okay? Because you don't always, even if there was only one row of input, you get output on other rows, okay? Because the filter is a 2D filter. So here, this block here takes the first row and produces the first row of output. But this block here, this block here also is not 0 because the second block of output will also not be 0. The second row will not be 0 because this filter has got more than one row in it, okay? So you can actually, so the best way to do this to get it set in your brain is to actually probably work out a simple case. Like maybe make up a 4x4 image, input output, and apply this filter and fill out the matrix. So if it's a 4x4 image, it's a 16 pixels, right? So then this matrix will be 16 by 16. So it'll be a 4x4 block of 4x4 matrices, right? And you can actually fill it out. Now, what will the structure of this matrix be?
Circulant block, circulant.
It'll be if this is a circulant filter, it'll be a circulant block, circulant matrix. If it's not circulant, if it's just truncated, then it'll be just toplets, block, toplets, okay? So that means the blocks will have a toplet structure, and each block will be toplets, okay? And so what will end up happening is, well, so essentially what would happen is that this was A, and this was B, and this was C, right? Those entries will go along here. This will be A, they'll fall along the diagonal. This will be B, and this will be C. And the same thing, this same block will be here. And then these will be 0. And over here, well, what would this be? This would be like the way the, let's do this one. This one would be the way the second row, where the first row impacts the second, okay? So if you're doing this sliding filter, you have to do flip and shift. I may have the B and the C reversed, actually. So going from left to right. Yeah. Oh, actually, I did it right. I think accidentally. Okay. And then this would be, if this is the impulse response, this would be E, F, and G, right? So the first row will, I might have this E, F, and G. The first row will now multiply by this, and the second row of output would be the inner product of the first row with E, F, and G. So what will happen is this will be like E here, and this will be F, and this will be G. And there'll be zeros here, okay? So you can populate this matrix from that filter. But yeah.
Oh, right, I think you might be getting to it. I was gonna say, didn't we agree earlier that, like, when we're implementing, like, the matrix implementation of this, like, trying to populate the matrix is just, like, kind of silly?
Absolutely. You were just saying, that's exactly my next point.
Sorry, yeah.
Once you've actually done this once, never do it again, okay? Well, actually, that's not entirely true. There will be applications where you really do have to construct this matrix, okay? But mostly the matrix is all zero, because if it's a large image, then there's only three, this is called a tri-diagonal submatrix, because there's only three non-zero diagonals. So if it's a big matrix, most all that's zero. It's incredibly inefficient to save this matrix in the computer with just all these zeros in it. Now that said, you can actually store this as what's called a sparse matrix. Matlab, for example, has a data structure which allows you to store just the non-zero entries, okay? So basically, you just store the index of the position and the value. You have pairs. So that's a lot better, but still, you can store this whole filter as just 9 values, right? So this is just very wasteful. But it is important to understand this, because mathematically that's how you manipulate it. And also, when you actually apply this filter, you need to apply it so that it's applied in a way that it actually produces exactly the equivalent result of if you had multiplied by the matrix. So sometimes along the boundary edges and things, different things will happen, okay? So you have to make sure when you, people will come to me and they'll say, well, what should I do on the boundary? Well, decide what your matrix A is here, okay? And in whatever your matrix A is, make sure you implement your filter so it produces exactly the same result it would if you had just populated the matrix, okay? Whatever your assumptions happen to be. If you assume that it's a circular matrix, then do circular convolution. If you assume that it's a topoless matrix, just a topoless matrix, then truncate appropriately, okay? But you have to do that consistently. You don't have to actually construct the matrix, but you have to apply the operation as if you had constructed the matrix, okay? Am I off the screen? Oh, I should have been standing on this side. That would have been better. It would be more interesting, perhaps. I don't know. Anyway, so do you get it? Now, in other applications, like for instance in tomography, you actually have to construct this matrix. Sometimes people will actually store the matrix. Sometimes, if you store the matrix, then that's called a stored. Well, it's called a stored matrix. Okay. And then the other possibility is you can actually do the computation on the fly. So when you never store the matrix A, what you do is you just write a function. You call it func A of X. And that's equal to, say, Y. So you never actually store the matrix A. Instead, you write a function which, when you apply it to X, produces an output which would be exactly equivalent to actually storing the matrix A. So this can be more in practice. If you look at the operations, usually you only multiply by A, or you multiply by A transpose. You don't necessarily have to ever construct A. A might be awfully big to construct, and you wouldn't want to have to store it. Okay? Does this make sense? So hopefully when you do this in the lab, this will go from being just an abstract concept to concrete. Okay? That you'll understand it. All right? Any questions about this? Okay, let me go to the document camera. Oh, that's the wrong thing here. Let me go to the document camera. Okay, there's the document camera, and so we last time I think we talked about the majorization. Let's see. So, okay. So, what happens is that this is the equation we talked about last time. So this becomes what we call the Q function. So if we're doing the optimization, and our current value of our current state of the optimization is x prime, right? And you say, okay, you take that, so x prime is a particular image, right? That's your current state of the image. And now you want to update x so that the value of x produces a smaller value of the cost function. So with that value of x, you compute this expression here, which is the ratio of the derivative. So for each pixel pair, you look at the difference between xs and xr, and you take the ratio of that difference to the value of the influence function, the derivative of the potential function at that difference. So you just calculate this, okay, and that's a coefficient that you use in the sum. And now you have a quadratic sum. So you take that coefficient, and this is equation 7.29, and then you have a sum of pre-computed weights times the quadratic difference between xs and xr. And now you have a quadratic optimization problem. So you can use whatever method you prefer. There's a wide variety of quadratic optimization problems, quadratic optimization approaches. In general, when you do optimization, you're first going to find a direction to minimize in, and then you're going to do line search along that direction. And remember, when you do line search of a quadratic function, you can calculate the minimum in closed form. So that's the key thing. Because now this is a quadratic function, you can calculate the update in closed form, so that the line search is efficient. And the price you pay for that is now you don't just do it once, right? You have to repeat it. So you're going to have a nested optimization. One optimization actually minimizes this function q, but even if you have the global minimum of the q, you now have to repeat that. And that's what this. Okay, so this is the majorization, minimization. You repeatedly, so each, if you look at figure 7.6, then you have an iteration, right? You have 10 iterations. Each iteration you minimize Q, but then to minimize Q also requires an iterative algorithm, typically, right? You can't minimize Q in closed form. So you might do, say, gradient descent or conjugate gradient. In fact, what you might do is you may not find the global minimum with respect to x. You might just reduce the value. You might do one iteration of gradient descent and then update. So it may not pay to converge all the way to the global minimum. So, but you have nested optimization. So this is another theme that you're going to have these nested do loops, okay, where each step of one requires iterations of the other, okay? So the computation can go real fast because of the nesting, so you have to be careful. You may only do one or two iterations of the internal update for each external update. It's what I call the Russian doll effect, right? So you have to keep this
straight in your head, because otherwise it can get very confusing. All right. Are there any questions about this? Yeah.
Is there just one, so for example, if you're doing this in 2 dimensions, then you have like an 8-point neighborhood system generally for each pixel. So that 8-point neighborhood, so it's not like you have 8, well, even if you have 8 Q functions, then you can sum them together, right?
Okay,
And
so
then,
this Q function
Represents the overall Q function.
right,
Right.
the sum overall 8, because
Yeah.
you can, it's a linear operator, right? You
That's
can
a
sum.
very good question.
Okay.
So,
That's what 7.29 is.
Yeah.
because each term in this sum is
Okay.
itself a
Yeah.
Q function,
But then, remember that one of the things I said here is that, that's this property 7.8, that if you have a substitute function
Yeah.
for f, then the sum of the substitute functions is the substitute function of the sum, right? So you can commute those, which is cool. So that's what happened here, that so now x is a complete quadratic function. Now it might be, if you're doing coordinate descent update, in practice you only really have to do this for one term. Okay? But if you're doing conjugate gradient or gradient descent, then you have to do it for all the terms. You have to do the substitute function for all the terms.
Okay. So,
actually, no, that's not true. In coordinate descent,
You don't just do it for one term, you have to at least do it for every neighbor, the term associated with every pair of neighbors.
yeah.
But for gradient descent, you have to do it for every pair of clicks in the whole image, okay? I know it's a little confusing, and people who work on this all the time, after a while they get good. It's like, you know how like kids that hang out together in like a clubhouse, they like create like a shorthand terminology and a lingo, and nobody knows what they're talking about. It's like Pig Latin, okay? You know what Pig Latin is? There aren't too many people who know what Pig Latin is in this room, probably. It's like when you there's some kind of algorithm where you add the word A or something to every word, so you go, help A, I don't know, little kids do it, okay? Because they think their parents can't understand what they're saying, okay? But their parents can. But in any case, it's a little bit like that. You have this whole culture of all these little things you do, and you add them all together, and then everybody else can be totally confused when you're talking, okay? Which is great value, because it means you're the only one who can do it.
It's very employable.
Now, so that's equation 7.29, okay? Now, then, it turns out that these expressions you can just calculate analytically for the different cost functions, and that's what's in this table, and hopefully those expressions are all right, so I can kind of debug them. So this tells you how you actually calculate.
Now, I'll warn you that for some of these things, you can run into trouble. Because if the
second derivative is unbounded, you can have a problem. I don't want to go into that too much, and there's a lot of alternative methods for fixing that, but it kind of gets complicated, so it sort of goes beyond the scope of what I'm going to teach in the class. If you actually get to that level of sophistication, then you can read other papers. But, and here I think we'll work out some examples. So you should read through these carefully so you understand how they work. So this is the optimization. I'm sorry, I should have turned off my phone. I don't even know how to turn it off. Okay. There it goes. Okay. Now, so this is now the general optimization strategy in figure 7.8. So what you do is you have an algorithm, with your favorite algorithm. The favorite algorithm selects I guess really there is a disadvantage to this, which is that I'm getting glare on the page. Am I getting glare on the page? Is this reducing the light intensity? No. It's not reducing the light intensity. But not on this one. See if this one helps. Yeah, that's better. Wow. Okay. Okay, so
you take your current state,
and knowledge of your function you're minimizing, and based upon that, you select
a direction for minimization,
and an interval. Okay?
so the gradient descent D here would
Would just be the gradient, the negative gradient.
if it's a more
Sophisticated algorithm, it would be some more sophisticated way of
selecting the direction.
okay?
Then you calculate these coefficients, the DSR,
As a function of the derivative of central functions, right?
so
Effectively, what happens
is that you're like using
a quadratic approximation for every potential function. The quadratic approximation guarantees convergence.
if you use any
Quadratic approximation.
one more.
So well. And then you calculate the first derivative.
Theta 1 is the first derivative in the direction D, and theta 2 is the second derivative in the direction D.
And then once you have the first and second derivative, well, you know, if you know the first and second derivative of a function, you know that the change in the function is the ratio of the first derivative to the second derivative. That's just Newton's method. Let me draw that picture. That was the picture I drew yesterday. So you have
Some function like
that, and you're doing, oh no, I'm doing it wrong. Never mind. So we're doing minimization, right? So you have a function like this, right? And let's say you're here, okay?
so the derivative is positive.
So you know here, this is
That's the value of the derivative, okay? And this is the value of the
second derivative. So you just,
so that's the second derivative is going to be theta 2, and the value here is
theta 1, right? So then you
just draw the line, and this is the current value, we call it alpha. So the new value, alpha star, or no, I'm sorry, this is, okay, your step is always 0 initially, okay?
so this is alpha star.
So alpha star is going to be just equal minus theta 1 over theta 2, right?
Except, in addition, you have to clip it if it goes to the interval AB, because you have some constraint that you know that it has to fall in that interval, okay?
Keep it moving. Yeah, you get you're off the screen.
Oh, I'm off the screen, thank you. Okay, so alpha star is really going to be the clipping of minus theta 1 over theta 2
And AB.
Okay. So that's the update here. And then the new, this is the D alpha star, but that's not what it is. It's
The new update of X then is the old
update of X plus
D times,
the scalar alpha star. And that's the update then.
and then you just repeat. Does this make sense in
Concept? This is the general structure of
most optimization algorithms? You start off by figuring out what direction to move in. If you're going to do the majorization, then you
calculate these coefficients, okay, these quadratic coefficients
that give you
the quadratic substitute function. Then you compute the first derivative and the second derivative.
This is the first and second derivative of the Q function, right? You can get these by just
Look at the notes, you'll see that they're correct, hopefully. If they're not correct, please tell me, because I'll correct them. And then once you know the first and second derivative, you can do the update. This is basically a Newton-Raphson step for the quadratic function. And then you update X, and then you repeat. Does that make sense? And in the particular case of coordinate descent, in coordinate descent, it's a special case where the direction is you only change one pixel at a time. So the vector, which is all zeros except for 1, 1 in one position. Okay? Are there any questions about this? I fear that it's a little bit complicated. I also have a section here on positivity constraints, but I'm not going to talk about that too much because it gets a little complicated. I feel like we need to move on, but you should read this material. There's also here, this is a handy-dandy little thing. There's this idea of joint math estimate, okay? It comes up a lot, and it's quite useful, but it's a little bit theoretically unsound, because it could give you some problems in certain cases, but in most cases it works pretty well, but it's really handy. And from an engineering perspective, it works great, okay? So, if you have some kind of distribution, and you have a P of, say, y, x, but it's also parameterized with theta, and you don't know theta. So you have to estimate theta along with, your objective is to estimate x, but you need to estimate theta too. This is called the nuisance parameter. So it's something you didn't really care about, but you had no choice but to know. So for instance, this might represent the focus of a camera, okay? So you wanted to, or the point spread function in your system, or it could represent the unknown noise variance, okay? It's some unknown about your system. What you need to have is some calibration parameter you need to have in order to effectively estimate x, but you don't know it. So you need to estimate it along with finding x. So what you can do there is you can say, okay, well, I'll take the log of p of y given x, and now theta may typically, in a lot of cases, theta only parameterizes the conditional distribution of y given x. For instance, if it's a parameter like focus, it's a property of the instrument, right? So then actually I use the letter, in that case, phi in the middle. So I use the letter phi for any parameter of the instrument, and minus the log of p of theta of x. So what you do then is you do the arg min over x and theta and c. So that's not strictly, and that produces an estimate, x hat, theta hat, c hat. That is not the map estimate anymore, because the map estimate, it's neither the map estimate nor the maximum likelihood estimate. It'd be sort of like the map estimate if you assume some distribution for phi and theta. Okay, it's sort of like an unholy combination of the maximum likelihood estimate and the map estimate. Okay, but it's really neither. Nonetheless, in some cases, it can be pretty effective. It's a good thing to keep in mind. Particularly like estimating parameters of the forward model. And that comes up a lot in applications because you have calibration parameters of the system you need to know. So the noise variance estimation, so I'm going to skip all this, even though it's pretty useful stuff. You should read it. And I think with that, maybe, I could either talk more about some of this material, answer some questions, or maybe I can start talking about the EM algorithm a little bit, because it never hurts to spend a little extra time on the EM algorithm. Okay? So the next section is the EM algorithm. There's a few reasons I covered the EM algorithm next. One is because by this time you're pretty sick about hearing about the map estimate. Okay? And you're struggling with trying to implement the lab, and so I just kind of move on. The other thing is that this method now is really kind of derived out of this majorization approach. Because EM algorithm is a special case of a majorization algorithm. And the other thing is EM algorithm is really important because it's really fundamental to modeling of data. It comes up in a lot of applications, and more importantly than that, because it's often the case that the EM algorithm can be replaced with some other method that can even be more effective and more efficient. Okay, but the thing that's so important about the EM algorithm, it gives you a conceptual framework to think about problems. So more than just as an algorithm, it's really kind of a whole way of thinking about problems. Okay. There's lots of different ways of thinking of the EM algorithm, and you really only understand it after you understand all the ways and how they fit together. Okay. And frankly, okay, well maybe this is true, but I think it is true, that I think there aren't a whole lot of places to learn the EM algorithm well. So very few people really understand it well, although that group is growing. And this is one of the few places to learn it. So I really want everybody to come out of this class with a fundamental understanding of the EM algorithm. Okay? Now, the EM algorithm is a little bit like New Shimmer. Okay? I don't know if anybody's ever heard of New Shimmer, okay, but it was, you can look it up, New Shimmer. New Shimmer. It's both a floor wax and a dessert topping. Not so dessert. This is it's topping. It's close enough. Given how ridiculous the conversation is to start off with. Okay? So these shimmers are both a floor wax and a dessert topping. Okay? So, and EM algorithm is a little bit like that. You know, the EM algorithm is both, it's an algorithm, it's a theoretical framework, and it's an optimization approach. So it's a lot of different things, and you need to sort of understand. Most people understand the EM algorithm just as an algorithm. Like they think of it like the way you would think about a washing machine. Okay? They go, okay, how do you use a washing machine? Well, you push the on button and you turn it to like the normal cycle with the spin. Okay? So they just dial in the thing and they push go. Okay? And that's how they use the EM algorithm. But they don't really understand what they're doing. Okay? So the problem is that's fine when the washing machine works fine. Okay? But if the washing you start having problems with the washing machine, it's overflowing, then you don't know what to do. You're saying, well, you keep pushing the on button, but nothing's happening. Okay? But as the people in this class, you guys are supposed to be the people who really understand what's under the hood. Okay? And can make the thing work. All right, so that's why I'm going to expect you to understand it in more depth. Now, okay, the best way to start understanding the EM algorithm is, I think, the best application is clustering. Okay, so the following thing happens. So you have, sometimes it's hard to come up with what appears to be a reasonable example here, but okay. So let's say. So what you did is you had a bunch of plants. Okay, that's a plant. And now what you did is you randomly, when I say randomly, so for each plant with probability something or other, okay, let's say probability 1/2, you either fertilized it or you didn't fertilize it. Right? So you selected, you flipped a coin. And for each plant, you decided whether it's going to get fertilized or not. Okay? So you wrote down on a piece of paper here. You say, plant 1, and I'm going to fertilize it. And plant 2, I'm going to flip the coin up, no fertilizer. Okay? And you have the list. Okay? And so you get the plant in, and then you have, I don't know, it's going to be fertilized. Okay? So you keep this list here, and you plant it. Now, what will happen is the first plant got fertilized. So it grew larger, okay? And the second plant didn't get any fertilizer. The last plant grew larger, okay? So what's going to happen now is, okay, so now you could plot the fertilized plant and it would look like this, right? That would be like the height of the fertilized plant, right? We'll call it Y. Okay. So for each one, you get some height, and it would have some distribution. And now you can look at the height of the unfertilized plant, and it would look different, right? It would look like, I don't know, like this, okay? Because they, on average, don't grow as high. But sometimes one of them grows higher than one of the fertilized plants, right? So there's some variation, random variation, and there's some overlap. Okay. So now what you do is you go, okay, so that's all good and well and fine, and you can model each of these Gaussian. So you can find the mean and the variance of the two Gaussians associated with these two distributions, and the total area in this curve would be, this will be 1, and the total area in this curve is 1. But actually, if it's a histogram, then it's really 1 time, the area is going to be 1 time the number of plants in that category, right? So now, okay, that's all fine and well, but now what happens is that accidentally, okay, you put this list in your drawer, okay, and when you were on vacation, your house burned down, okay? So there were flames and your house burned down, and you lost the list. So now all you know is how high the plants are. So all you know is that you have some distribution. But you did all this work to plant the plants, and you still want to figure out what the mean and variance was associated with the two different categories. And you say, well, it's too late. I mean, I had this unfortunate incident that the house burned down, and I don't have a list anymore. So how am I going to back out the estimates of the mean and variance? And you say, well, but let's say it was very expensive. These are very valuable plants, and you can't do the experiment over again. You need the data, okay? The exam is due tomorrow, and your unreasonable PhD advisor is insisting that you have the results, even though you lost the list, it got burned and can't be recovered. So what are you going to do? Well, any self-respecting graduate student in a situation like this of extreme desperation, okay, is going to look at the two distributions. That was the unfertilized, and this is the fertilized, right? Okay. You're going to say, well, come on. I got the distribution. It kind of looks like this. What I'll do is I'll say these must have been the fertilized, and the ones on the right have to be the fertilized, and the ones on the left have to be unfertilized, right? So I'll just put a threshold here, and anything above the threshold I'll say was fertilized, and anything below the threshold I'll say is unfertilized, okay? So, okay, yeah.
Do you know the mean? Like, do you remember the mean? In this case?
No, you don't have anything other than just the distribution, okay?
Yeah, but the distribution do have the mean.
Yes, but you don't know them.
Okay.
That's what you want to estimate. I want to find the average height of the unfertilized plants and the average height of the fertilized
You do know the
plants.
threshold.
Well, you don't know the threshold either, except for what you can do is you can just find a place that's in the valley here, right? Yeah. I mean, you're kind of hosed because the house burned down. So you've lost the information you're keeping, right? But you're going to just say, okay, well, I'm desperate, I'll draw a line here, okay? Now, the problem is this. You say, what you do is that, okay, so now you're going to estimate the mean. But is the estimate of the mean going to be accurate?
Could be too close to the middle.
It's going to be wrong, right? I mean, like, let's say we did the following. Let's say I want to do an experiment and determine if people who like Charlie Bowman are smarter, okay? Okay? So what I'll do is, like, I'll say, well, if you're smart, you must be in the category of people who like Charlie Bowman, okay? Okay? And if you're not smart, well, you must Okay, if you don't like Charlie Bowman, well, you must be an administrator. Okay, no, okay. Whatever. Okay, I'm going to cheat, right? If I make the assumption that smart people like Charlie Bowman as a precursor to figuring out what the average intelligence of people who like Charlie Bowman is, I'm going to find that I'm going to have a biased estimate, right? I'm sort of, it kind of reminds me a little bit. Does anybody have a coin? When you were a kid, when I was a kid, one of the favorite things that my friends used to do is this, okay? They would do this. Does anybody have a coin? Okay, yeah. Coin in the coin. Okay, this is what they would do. They'd say, okay, we're going to play a game, okay, and I wanted to play baseball, and they wanted to play football, okay? Okay. So they say, okay, well, we'll decide who plays, okay? If it comes up heads, we'll play the game you want to, we'll play the game I want to play, football. If it comes up tails, we'll play baseball, okay? So what they did then is they rolled it and they go, oh, it came up tails. Okay, but, so I'm like, so I won, right? And they go, well, yeah, okay, but I didn't throw it right. Let me try again, okay? And they go, oh, it came up tails again. Oh, no, but I made it say, oh, it came up heads. I win, okay? So if you let me keep throwing the thing, until it comes back the way I want, well, of course I can get the answer I want. I'm cheating, okay? You're cheating here because you're assuming that you're throwing a threshold, and you're throwing away anything below that threshold. So of course you're going to get the result that the fertilized plants are taller, right? That said, so you say, well, this is hopeless. I can't do it. Well, that's not true either, because if I look at this, it's pretty clear that there's a distribution there. I should be able to somehow extract the mean. Now, the problem is this, and this is your coin back, okay? I'm sorry. You can get that. But the problem is this. This is not just a bias estimator. This estimator is inconsistent. I can have an infinite amount of data, and my estimate of the mean and variance of these distributions will be wrong. A bias estimator is one where the expected value of the distribution is wrong, okay? But bias estimators are still usually consistent. A consistent estimator says that as the amount of data goes to infinity, the variance of the estimator goes to zero, the mean square error. But that's not true. Here, I can have an infinite amount of data, and I'm going to calculate the wrong mean. So how do I get around that? So what you want to do is, so the EM algorithm gets around that. The problem is this. So we have xn, okay? This is the label. The label was fertilized or unfertilized. It's a binary label. And we have yn is the height. If we have x and y together, we could solve the problem. All we would do is sum all the y's corresponding to a particular value of x, and we calculate the average, and we get an estimate, we get a consistent, unbiased estimate of the mean of y for that category. The problem is we lost this left. We have incomplete data. So it's called incomplete data. So y is called the incomplete data. Y and x together are called the complete data, right? And so EM algorithm is a general approach to solving problems with incomplete data. And the trick is this. Well, okay, so intuitively, our approach here was on the right track, but we kind of did the wrong thing. The idea here is we're trying to estimate x, and then use our estimate of x to determine the mean of y. But here, our estimate of x, so the way we're estimating x is we're taking the value of y, and we're classifying it as either fertilized or unfertilized based on the value of y. So the question is, can you do that in a self-consistent way? Well, the answer is yes, for sure. Now, first of all, you could do the following. If you have, we're kind of running out of time. But you have t of y and x, okay, and then the unknown here is the parameter theta. First of all, we integrate out x, and then do the maximum likelihood estimate. So that's what we're going to learn how to do next time, okay?
So the trick with the EM algorithm is that we're going to try, we have a cycle in which we can bootstrap ourselves up and do what appears to be the impossible by estimating X from the data and then using our estimates to estimate the mean of Y. So read it. You got to read the note on this.